Hi everyone, we discussed the three empirical gas laws that relate P, V, and T in a prior video. In this video, we will start with a discussion of what many call the fourth gas law, which is Avogadros Law. In the other three laws, the amount of gas is constant. However, when we run chemical reactions, the amount of gas, measured in its number of moles, will change. This is what leads to Avogadro to propose his observation. Avogadros' law states that if pressure and temperature are constant for a gas, then the ratio of its volume to its number of moles is going to be constant. In other words, V over N is constant. N is the symbol we use to denote the number of moles of the gas. We can write Avogadros' law mathematically as V over N equals a constant, or similarly to the other empirical gas laws, we can write it as V1 over N1 equals V2 over N2 equals a constant. The key condition here is that P and T must be constant for the gases to have this relationship. We observe Avogadros' law in action when we inflate a balloon. As we add more gas particles into the balloon's volume increases. What's more important about Avogadros' law is that 1 mole of all gases at a given pressure and temperature condition should have the same volume. By convention, scientists choose the condition 0 degrees Celsius and 1 atmosphere as the standard temperature and pressure. This is also known as STP. At STP, the volume of 1 mole of any gas is 22.4 liters. This quantity is known as the molar volume of a gas at STP, 22.4 liter per mole. The molar volume is just the volume of 1 mole of a gas.
Let's work out this example on Avogadros' law. It says that you have a 2 liter of gas sample at 0 degrees Celsius and 1 atmosphere with a mass of 3.94 grams, and they want you to calculate gas density and the molar mass. So density, just like anytime you calculate it, requires you to divide the mass over the volume of the substance, and we're already given both those numbers. So let's do 3.94 grams over 2 liters, and our answer ends up being 1.97 grams per liter. Now, molar mass, remember, is the mass of 1 mole of a substance. So if you want to get it, you're going to have to take the mass of the substance divided by its number of moles, which has the symbol N. To get the number of moles, we're going to need to think a little bit about the situation that we're given. We were told that the gas is at 0 Celsius and 1 atmosphere, which is our STP condition. And at STP, 1 mole of a gas is going to have a volume of 22.4 liters, so we can use this as our conversion factor, either that or that. In this case, since we're trying to get to the number of moles in our calculation and then later on divide mass by it, we should first use that conversion factor for STP, which is 1 mole in every 22.4 liter, and then try to figure out that the number of moles in 2 liters of the gas. And if you calculate this out, you would get 0.089257 moles of the gas, and then it's just a matter of plugging that back in to calculate the molar mass, which is 3.94 grams being the mass and the number of moles that we just calculated. That should give us 44.1 grams per mole.
Once we have the four gas laws, we can see that they form the relationship among four gas properties: pressure, volume, temperature, and number of moles. We can combine these gas laws together into one equation written as PV over NT equals a constant. When we calculate the constant, we get the same value for any combination of PV, T, and N. This constant is what we now call the universal gas constant, or the ideal gas constant, and it has the symbol R. The value of R is 0.0821 liter atmosphere per mole Kelvin. The ideal gas equation can be written as PV over NT equals R, or more commonly, you will see the equation written as PV equals nRT, and this is called the ideal gas law. Keep in mind that if you're using the ideal gas equation, or anytime you use R in your calculation, you must use specific units for P, V, T, and N. Pressure must be expressed in atmosphere, volume must be in liters, the unit of T must be in Kelvin, and N is in moles. This is so that those units can cancel with the unit of R.
We can work through this example of an ideal gas type problem. It says here to calculate the number of moles in a basketball that's inflated to a certain total pressure with a volume at a particular temperature. So this is really pretty much straightforward ideal gas equation problem. You start with your ideal gas equation and you're trying to solve in this case for number of moles, which is the variable n. So we're going to have to divide both sides by RT, and that would allow us to isolate n, which is going to be equal to PV over RT. Now, the main thing to do here is to make sure that all the units can cancel with the units of R. So if I have 24.2 psi as my pressure, I need to look up the conversion factor between psi and atmosphere, which is the unit of pressure in the gas constant. And this happens to be 14.7 to 1 if you look it up. And then the volume is 3.2 liters, and that's already in the unit that R has, so we don't need to change that. R itself has a value of 0.0821 liter atmosphere per mole Kelvin, and then the temperature has to be in degrees Kelvin. So when this is done correctly, all the units will cancel out, leaving you with 1 over mole, which of course becomes just moles. And that should give us 0.215 moles.
The empirical gas laws and the ideal gas law we discussed were all based on observations. To explain why the gas properties are related the way they do, we need a scientific theory. This theory was fully developed in the mid to late 1800s and is called the Kinetic Molecular Theory of Gases, or abbreviated as the KMT. This theory shows that gases are composed of a collection of randomly moving particles with large distances separating one particle from another. The simulation here shows what the KMT assumptions are. Particles can collide or hit another particle or the wall of the container. The sum of the collisions with the wall is what the gas pressure represents. Because the particles are far apart, they don't experience attractive or repulsive forces that we would have expected. One of the major accomplishments of the KMT is the realization that the Kelvin temperature of a gas is correlated to the kinetic energy of the gas particles. Kinetic energy is the energy that results from motion. The KMT explains that when a sample of gas has higher temperature, that also means that the particle in that sample are moving at higher speed, thus having a higher kinetic energy. Similarly, if a gas is at a lower temperature, its particles are moving slowly and have less kinetic energy, as you can see in the simulation. There are equations that we can use to calculate the speed and kinetic energy of the gas particles at different temperatures, but we won't do them here. The wonderful thing about this KMT simulation is that we can use it to show the various empirical laws we've been talking about in this and other videos. For example, Boyle's law states that P and V are inversely proportional if the temperature and amount of gas are kept constant. Let's see how the KMT simulation can explain this. First, we hold our temperature constant. Since the container is closed, no gas particles can escape or enter the container, so the number of moles of gas is constant. Look at the pressure gauge. It tells us that the pressure is fluctuating around a value of, say, 3.7, 3.8. The reason there's a fluctuation is because the total number of collisions are changing. But what we're interested in is the average pressure that the gas sample has. Let's see what happens if we lower the volume to half its value. You can see that the pressure now increases to about double what its original value is. This is exactly what Boyle's law is telling us. Now the question is, why is this going on? The simulation shows us that as the volume decreases, the average number of collisions increases because there is less space for the particles to travel in. This results in an increase in overall pressure. That's the basis of Boyle's law. All the other empirical laws can also be explained using this simulation. I encourage you to check out this simulation and try out changing different parameters, temperature, pressure, and so on, to see how you can explain the empirical gas laws. The simulation can be found at the following website.